What's up, YouTube? This is Giant Jigglypuff 3 here. I'm going to be going over a general overview of what the ROM structure is for Banjo-Kazooie. This is not a how do I edit this asset tutorial. This is not a how do I edit the BK decomp tutorial. This is a here is where everything is located in the ROM, and if you want to look more into it, I will provide tutorials for those in the future. But for right now, a lot of people don't know how to even make edits to Banjo-Kazooie. So that's the start of what this tutorial is supposed to be. So let's go over a general overview. For the ROM structure, there are 4 parts that you probably will care about. There's more, but let's just go over these 4 for now. The N64 boot up stuff, the asset offset table, the asset files, and the assembly files. So I'll go over each one of those later, but know that the asset offset table is also called the asset pointer table, the asset table, other things along those lines. But as long as you hear asset and table, know that that refers to the location of each asset within the ROM. And I will be considering assets and assembly as different things. Assets being stuff like models, music, animations, map setups, stuff like that. Whereas assembly files are more of the code, and I'll be going over that more later. So, going into the N64 boot up stuff, what's in there? There's something called a checksum, which I will go over more right after this. The ROM name. So for the most part, your ROM's probably going to be called Banjo-Kazooie, and then whatever version it is. Initialize functions, basically saying, first do the checksum stuff, which again, I will explain right after this. And then go to this part of the code and start running it and start playing your game of Banjo-Kazooie. Then there's some other stuff you probably don't care about, like clock and stuff. And maybe if someone's deep into the tech, you can edit it. But if you know about that tech, you probably don't need this tutorial. So for right now, we're skipping it. Checksums, what are those? Who cares? So imagine you have 2 people, me and Bob, right? Bob and I have fingerprints. We each put our fingers into ink, and we print out our fingerprints, and they look different. Huh, who would have guessed? We are built different, so our structure, our composition as people is different, and that's a unique identifier, is our fingerprints. Now, for ROMs, and I will get to that here, ROMs also have these kinds of fingerprints, but they don't have fingers like we do, duh, right? Instead, the content of the file, so all of the bytes of the file, will be unique. And so, how do you calculate a fingerprint for a file? Basically, developers have an algorithm called checksums, which will go through every byte of the ROM and have a kind of algorithm to shorten it from this wide thing to a small string. The number of characters depends on the algorithm and how big the file is. But know that this algorithm is not universal. Any developer can make any kind of checksum algorithm. Windows has one, N64 has one, Banjo-Kazooie has one. These 3 are all different. And then there's plenty of other things that use checksums. So why do we care about checksums at all? So a checksum validates that your game is not tampered with. They calculated from, the entire file what they expect the fingerprint to be, and they will run a function later called an anti-tampering measure, which I'll get to later, that basically checks, does the contents of the file match this fingerprint that we had earlier? And if not, then you've tampered with the file. So here's an example, and I'm sorry I'm in the way. Know that these guys are zeros down here, and that's actually important that you know that. Let's say we have a 4 by 16 file, bytes of just zeros, and we'll call it 0.txt. And then we're going to modify this guy right here to be a 1. I know it's really hard to see. I'm in the way. Horrible tutorial. I don't understand anything. But know that this one right here at the very end is a 1. That's the only thing we've changed. And we're going to make 2 versions of it. We're going to make the zeros plus 1. And we're going to make 0 plus 1's copy. So they're different names, but they're the exact same content. If I were to run the Windows checksum command for this, right? You will see that zeros, first of all, if I run it twice, if I repeat it, they're the exact same checksum because it's an algorithm. It doesn't change the time of when you do it, but those two are the exact same. But the zeros and the zeros plus 1 have completely different strings that print out. Do you see the C8, D7, whatever for line, the second one, or the first one as well? And then the third one says AAE8, whatever. Those are the fingerprints, in this case called checksums. And you change one value, no matter how small, and that entire string changes. It doesn't matter how many times you calculate the checksum, it will always be the same as shown in the first two. And then it doesn't matter if you rename the file, as long as the contents are the same, the checksums will be the same. So you'll see that these guys are the exact same. So what are anti-tampering measures? So Nintendo sees that you try to change it so that Banjo-Kazooie has L to levitate. They don't like that. They don't like unauthorized versions of the game running on their console, because if the console were to blow up for some reason or go on fire, right? And they're like, send us a copy of your game, and they see that you mess with it, we don't owe you any liabilities. But if it was their copy of the game, then they have to go back to Rare and be like, yo, you guys have shot out a game that blows up. What's going on? So in order to save their ass, basically, they make these anti-tampering measures to try to make so that you don't mess with their game and then sue them later saying, hey, my N64 blew up. Banjo-Kazooie also has anti-tampering measures, but theirs are funnier. So for the N64 one, if the checksum doesn't match, nothing runs. You'll just get a black screen. For Banjo-Kazooie specific ones, Rare decided it'd be funny if they just fucked with you, if they changed your physics, if they changed your control scheme, if they removed moves from your character or your save file. So thanks, Rare. So how do we get around a checksum? We can either recalculate the checksum, but that requires us to know the algorithm, or we can remove every instance of that checksum being checked. And there's going to be a lot of them. So I'm just going to go over these two methods in more detail. But for the N64 one, I gotta remember who it was. Maybe it was the Super Mario World team. But the N64 CRC tool version 2, bless their hearts, they made a checksum algorithm or calculator, more or less, for every N64 game to recalculate the checksum if you've modified the first megabyte of the ROM, which for Banjo-Kazooie's case is the asset offset table. Now, that's only important if you really move around assets. If you don't really move around assets and stuff, then you probably don't even need this checksum. But it's good to have anyway. It's good to recalculate. So I'll get into more of what that is later. But that is a limit of the N64 CRC tool, is that it only checks for that first megabyte. And it's only for the N64 check, not the Banjo-Kazooie check. Banjo-Kazooie has a different algorithm entirely, and it's in different parts of the game. So if you want to calculate the checksum for Banjo-Kazooie, this is specifically what you would be running, and this is in Python. If you don't understand it, hit me up. I can try to explain it. It's not pretty. It doesn't look better in anyone else's version of it. They all kind of look like this. But the one thing that's unique to Banjo is the CIC. Now, the CIC is a made-up acronym by the modding community. So I don't actually remember what it stands for, but the A3886759 is unique to Banjo. Everything else, I believe, is N64 related numerical values. Um, the calculate the new CRC, there are some functions in there that actually depend on which game you're doing. So I even have all those functions. I only have the ones that pertain to Banjo-Kazooie. So if you're trying to run this for SM64, this algorithm will not work. Heads up. Now, how do we ignore checksums? So what's gonna happen? It's gonna say, we're gonna calculate this entire section of the game, this content, and we've already made a fingerprint of what we expect to see, right? If that fingerprint does not match what we just now generated, they don't match. So what we can do is remove the function that checks it entirely. We can either make it always true and say, oh yeah, they always match. Yeah, we got it. The checksum's fine. Or we can just white out the entire section. That's fine too. Both are easy to do. I actually kind of like the true one because it's kind of funny. It goes through all the work of calculating the checksum. And all you have to do is change a branching from check this to, oh yeah, just skip it. Whatever. That's fine. But the issue with this is that there's a lot of these throughout the entire ROM. So you'd have to find every instance of it. Shoutouts to Wetarobi. He implemented a bunch of these disable anti-tampering stuff in the randomizer, and I do have a list that I can help people out with if they need it. He doesn't know if it's all of them though, so still shoutouts to him for getting as many as he could, if not all of them. The list of known checksums that we know so far are in Core 1, which I will explain what that is more later, but Core 1 will basically, if you mess with Core 1 or Core 2, your joystick will only move at half whenever you move it all the way full, which prevents you from changing save files. It prevents you from running. I'm trying to think what else it changes, but it messes with you more than you think. I don't remember what Mumbo's Mountain, Clinker's Cavern, Bubblegoo Swamp, or Gobi's Valley do, but Treasure Trove Cove will make it so that at a lockup, I think the checksum is actually hidden in a lockup function. Shoutouts to Jumbo for that one, by the way, for finding that. Is the game will prevent you from on the floor changing your momentum. So you start running and you'll just keep running that direction until you jump in a different direction, which then you start sliding that direction. It's a whole mess. It's really funny. Mad Monster Mansion, I believe they removed 2 moves from your save file, which I think is really funny. But basically all these have a way of fucking with your game. Shoutouts to Rare for being funny about the checksum stuff. Now, what is the asset offset table? Which someone might just say the asset table because it's easier to say. I'm stumbling as I'm saying it. So first we have to understand what is an offset. And to explain an offset, I'm going to compare it to an address. So an address basically says, this is the location of the thing in the ROM. Done. So for example, if I were to say my longitude and latitude are 0 and 0 on the globe, I would be at the equator and, you know, like right at the center of like the map, right? What an offset is you have to know where the actual information starts and then have a address from there. So, for example, if you think of streets in America, they have an arbitrary, like, random address, and it just increases from there. And that would be the offset from that starting address. So, this is a file, and I don't need to uncover myself because I'm not really covering anything important, right? And I labeled all the index positions, but let's say we have this file, and the address is at 08 hex. That's it. we're right there. We're done. No need to do anything else, right? But if we have an offset, we need to know where the offset starts from. So let's say, as an example, we start at hex 10, right? Or 10 if you don't want me to say 10. If I were to say the offset is 08, we would start at 10 and we would add 08. So we would go all the way to hex 18 or hex 18. So what are the asset files? So here are listed some, I'm gonna point this way. Here are listed some of the examples of what an asset file is, but basically these are static files that are parsable. What does parsable mean? Basically, we can break down these files in a specific structured format. So they are structured, and if you ever look at the decomp, right, you will see something called a struct. A struct is just a structure of how something is formatted. Think of it like a blueprint in a sense, or a class, or like if you think of like chess pieces, right? You can think of a piece as like an asset. Now, what is that piece? Is that piece a pawn where it moves a certain way and attacks a certain way? Is it a queen where it moves a certain way and attacks a certain way? Etc. They have a structure to them. So we have animations, models, setup files. I'm not going to go through the whole list. There's a bunch. You can read. Now, the asset offset table is the offset from the start of where the assets start. So in our case, by the way, it is hex 10CD0. That's where the assets start. And the offset table will say, go this many bytes from that to find your asset. And it is a linked list. Those offsets will always increase. They will never decrease. If they ever stay the same, that means that that asset itself does not exist. It is 0. There's nothing there, nothing being used. But it'll always increase, and the ID of it, you can think of it like a file ID, gets increased by 1 every time. This file ID, we can call it as an enumerator, or sometimes you will see it as enum, E-N-U-M. And these values are just digit values to represent that asset. So the asset table starts at 5E90 hex and ends at 10CD0, like I said before. Now, every 8 bytes has 4 bits of information, or sorry, 4 bytes of information that we understand, and 4 bytes that we're still trying to figure out to this day. But those first 4 bytes are the offset from 10CD0. So if the offset, for example, is 100 in hex, you would add 100 to 10CD0 to find the location or the address of the asset itself. Now, we have speculation on what those other 4 bytes mean. First 2 bytes might be whether it's decompressed or empty, or whether it's compressed. We don't know. And then the last 2, we have no clue. It's like 4 values it could be. We're not sure what those mean. So, moving on from there. What are assembly files? So, the game was compiled in C, and C is a compiler language. So, it goes from human readable to machine code. In our case, the machine code is MIPS. And that's one easier for the N64 to read and go faster, navigate, because it's already in machine code. It already understands it. It doesn't have to translate anything. Python, for example, is a interpreter language where every line of code would need to be interpreted and turned into machine code on runtime, whereas compiler is already ready. Now, there are 4 different kinds of files, and I'm going to phrase it like that, but they include the C libraries, which is core 1, the game engine, which is core 2, and I'll get to what those 2 are in a bit, the level and layer specific code. So if you are in the layer, it is different than if you're in a level. It's different than if you're in a different level. And those are all different from if you're in a cutscene. So, for example, if I'm in Mumbo's Mountain, I have access to Mumbo's Mountain specific things like Grublins, Conga, Chimpy, and Juju. Now, what is something in Mumbo's Mountain that is not specific to Mumbo's Mountain are tickers. So those exist in Mumbo's Mountain, the lair, and Freezy Peak. So that tickers are actually not in the level specific code. They will be in game engine, which I will get to later. Cutscene code is like Dingpot by the bench, who is the nicest looking wench. Like it's that cutscene, like the intro cutscene, the game over cutscene, stuff like that. Now, what is the difference between C libraries and game engine? Because C libraries, remember, is core 1, game engine is core 2. C libraries is the generic computing functions for any N64 game, whether this is like how to calculate a array going from like vision, like line of sight or whatever, right? Or whether it's point straight down or calculating the distance, from an enemy, handling the memory, playing audio, decompressing files. These are all generic N64 things. It is not specific to Banjo-Kazooie. Game engine, though, is specific to Banjo-Kazooie. It's the general game functions. So remember how tickers are in 3 different areas of the game, right? So you could put tickers in Mumbo's Mountain, the specific file, the Freezy Peak specific file, and the lair specific file. Or you can have a general common place that all 3 of those can pull from, in this case, the game engine. So things like warping the player, because that's not necessarily specific to Banjo-Kazooie, but the way they do it is different than other games, possibly. Global enemies like tickers, beehives, big butts, etc. The pause menu is another example, because you can use the pause menu anywhere. Those will all be in game engine. And I kind of went over what would be a level specific one versus what would be a game engine one, but know that if you can kind of think about it, right? If you can imagine something in multiple areas of the game, whether it be Mumbo's Mountain and the lair, then it's a game engine thing. It's probably in both. Now, if it's only in one, so for example, if I was to think of Muty snippets, right, versus snippets, because snippets you see in Clanker's Cavern and you see in where else do you see snippets? Rusty Bucket Bay. Oh, this is a bad time to blank out. I'm blanking. Let's go to a different enemy. Let's go to Flibbits. Right? Flibbits are only found in Bubblegoop Swamp. You don't see them outside of Bubblegoop Swamp. Not even in the lair outside of Bubblegoop Swamp. But you do see Chompas, like the grilled Chompas that come out of the, little grill thing. Good explanation, Jigglypuff. You see those in both the lair and multiple levels. So that would be a game engine enemy. Specific minigames like Mr. Vile, Tumbler, those are all specific to levels. You don't see them anywhere else. And then there are some specific flags like the sandcastle. Have you done the jiggy or whatever? If so, make sure that the gate's up. Clanker, have you raised Clanker? If so, and you raised Clanker and got the jiggy. If so, make sure Clanker's up at the start of the level, etc. like that. So, assembly files are not just one file per level. There's 2 parts of it. There's the code part, which is like the actual functions themselves. And then there's the data portion. So it's all the static values. So for example, for Banjo-Kazooie, there is the data of how fast is Banjo, how high does Banjo jump, what scale do we scale his model to, versus the actual walking of like play this animation and move at the distance of the data value of his speed, whatever that we got earlier. At what point do we go from like the, little kind of push thingy, like the crawl, not crawl, like creeping kind of walk, to the walk to the run, stuff like that. Okay, so the all Banjo-Kazooie files are read decompressed, and those are the either whether it's a asset file or a assembly file, those are read as decompressed files. However, in order to make space in the ROM, they are compressed down to whenever they are actually needed. And not every file in the game is compressed. Some of them are generically decompressed. I'm guessing in order to quickly access them because they're globally used, right? Like some things on the pause menu are typically like always accessible and like decompressed. But things like an enemy might not be because there's no, that enemy might not exist in every. Well, that enemy doesn't exist in every area of the game, as an example. So, most files, and I already touched over this like a little bit, but most files in the game are not used all the time. Do you always need Gruntilda's model to be loaded up? No, you don't. You don't. So you can zip it up and decompress it whenever you actually need to. And if we had everything loaded up at the same time, it might be too big for the RAM to handle. But at the same time, we need to read those files at some point, so they get decompressed, whenever they are actually used. And to indicate that it is a compressed file, they all start with 1172. And I believe, okay, so it's either 1172 or 117200, which it's theorized. I'm not sure which way, one way or the other, but if it's 1172, then the next 4 bytes is the size of the decompressed file. Now, if it's 117200, then the next 3 bytes would be the size of the decompressed file. We still don't fully understand that, but no file has been big enough to need all 4, so I'm still going ahead and saying it's 1172 and 4 bytes. And then after that, it's the compressed version of the decompressed file. So how do we decompress these files? So the only way that I'm aware of how to do it is by using an algorithm of gzip. So gzip is a compression tool. Python actually has a gzip import library that you can use in order to also compress and decompress files. There's an external tool that you can use on Windows command line, and we compress it at level 9 for Banjo-Kazooie. Now, when we are extracting or replacing asset files, so this is the main process. I'm going to be kind of reading it verbatim, but basically we're going to find the assets asset offset table index. So where in the asset offset table is this asset? Once we find that, we take that offset plus the next offset to find the start and end location of that asset. And to find the address, we take the offset in the asset offset table plus 10CD0 in order to find the address, and we pull that start and end out of the ROM. Once it's out of the ROM, it should be the 1172 plus the 4 bytes of the size plus the actual compressed file. So we'll take that compressed file section and decompress that using gzip. To insert it back in, we kind of just do the reverse. We add the 1172, we add the decompressed file size. At the end of the compressed file, we need to make sure that the length of the file is divisible by 8. So we would pad the file with AA up to the 8th byte. Once we do that, we can insert it back into the ROM. And remember, this is, the assets are in a linked list, so they have to be in order. So we can insert it back to after the previous, but before the next. we adjust the asset offset table in order to account for the new offset, and then we recalculate the N64 checksum, which is at the beginning, which again checks the first megabyte of the ROM. Now, there is an issue with inserting asset files, and this is why I don't necessarily like using GE decompressor. If you were to try to put everything back into the middle of the ROM, if a file compressed larger than the original size for some reason, the compression algorithm, then we would have a hard time fitting it all back in, which is annoying. Sorry, my dog's standing up now and distracted me. So we have to make sure that whenever we insert it back in, it has to be the same size or smaller. There is a workaround though. Linked lists do not care where they are in the ROM. So we can actually take all those assets and just append it to the back of the ROM and then point the offset to the end of the ROM, back at the very back. That way, there is no end index that we have to go to. I mean, sure, you don't want your ROM file to be huge, but we have plenty of room to work with. So you can just insert the back and then have the asset offset table point to that, and it'll still work fine as long as they're still in order. So to append, the steps are mostly the same except for number 3. Insert every asset file at the back of the ROM or append to the back of the ROM in their original order, and then update everything else. Now for extracting and replacing assembly files, this one's actually a bit different. So we don't actually know what determines where the assembly files start. Now, remember the N64 boot up stuff? Somewhere in there is the addresses of these assembly files, and I believe, shoutouts to Minins, Mr. Patcher, which is a program that he wrote, has these locations. However, it does not work. I have tried it, something breaks, and I'm not sure if we're missing something or whether there's some kind of checksum that goes with this, but there's something that does not work with that. So until then, I'm going to go ahead and say we do not know. So until then, extracting is more or less the same, except remember that there is a code part of the assembly file and a data part, and it's not separated out by those paddings. At some point partway through, you'll just randomly see 1172, and I think for some of those assembly files, you'll see 1172 show up multiple times, which is why I say look up 117200, because that shows that that's where the size of the ROM, and there should be only one of those for each of the files. So split it from that point on, and then decompress both those parts using the same algorithm as before. And when we're inserting it back in, same thing, except now we have the compressed file, the compressed code file, and we append the data immediately after. There's no padding in between. Immediately after, and then we pad the file. I think their convention is 0000. I don't know if it actually matters, but go ahead and just keep it at 00 for the padding, up to the 16th byte, not the 8th byte. Assets 8 byte, assembly 16th byte, and then insert that back into the original location of that assembly file. Oh, I have the word asset here. My bad. Copy and paste. Ignore the asset file on the very top of the thing. But limits. We don't know how to move these assembly files, and we don't know how to increase the allotted slot. I actually don't even know if we can use up less space for the assembly files. I just know that we can't go more. So be careful on that. But yeah, that's all I have. There's no quiz show for this one. There's too much to talk about. I'm actually on a busy schedule, but this video needed to come out because the decomp was worked on by like 0.1% or something small, but it's enough to get people excited for the decomp to come out. And people are wondering what the heck Core 1 and Core 2 meant, and people are asking questions. So this video is doesn't even go over the decomp yet. But it is the start of how to understand the decomp itself. So thanks everyone for watching. Hopefully this helps someone out, and have a good weekend. Bye.